Good afternoon, everyone. We talked last time about bearings of the plane type, and this is going to discuss rolling element bearings. On your project, I've asked you to design bearings to support your shaft, and in this particular instance, the type of bearing we talked about yesterday is not too appropriate. And the main reason is that this machine is making a personal product, and I can't let oil get on the product. And the type of bearing we discussed the other day needs a lot of oil. So you'd either have to put it in an oil-tight box and seal it and that sort of thing, and then provide some oil flow to replenish to make sure it didn't run out of oil, because this is vertical. And that's just not practical. So this is an application in your project for a roller-type bearing, which should be a ball bearing or a roller bearing of some sort. So that's what this lecture discusses. It's also in Chapter 11. It's the second part of the chapter. I think I showed you this picture before. It's just a picture of a gearbox. I think we looked at this when I was talking about gears. But this shows the bearings that support the shafts that are in the gearbox. And these happen to be tapered roller bearings at each location, which are very nice bearings because they give me both a radial and a thrust component, so I can support both the axial load, if any, on the shaft, which there would be if these were helical gears, and also the radial loads. This shows double row ball bearings in both locations. It's a note here that says they're sealed. Lubrication system consists of a grease nipple, so you come around with a grease gun and squirt some grease in there. So grease rather than oil is typically used to lubricate this type of bearing. And you can buy these bearings off the shelf with seals to prevent the grease from getting out, and so-called lifetime lubrication, in quotes, which is its lifetime, not yours. So in that respect, they're handy because they're an off-the-shelf item. They're not terribly expensive considering the technology that's involved, because they make them by the millions, and they've invested a lot of machinery in the manufacturing process, so they're fairly inexpensive. They're made by a wide variety of manufacturers all over the world, and they're made to international standards, which means that any manufacturer's bearing of the same category is interchangeable with anybody else's, so you're not locked into any particular manufacturer. Same as with gears. So ball and roller are the general types, and within those two general categories there's a whole big variety. For example, here we have this category of radial ball bearings, radial meaning that they're going to take radial loads and not very much thrust load, if any. Then there are those that are made specifically to take thrust. Then you have roller types, which can be either radial or thrust or some combination thereof. Here's that tapered roller that will take both side loads, that's thrust loads, and radial loads. So these are some closer views of ball bearings. On the left is a so-called deep groove ball bearing. It's also called a Conrad type. It's the most commonly used. It has the highest speed capability of any of these types of bearings. You'll notice that there are grooves that match the radius of the ball for some portion of it, both on the outer and the inner ring. Everything here is hardened steel. They use a high chromium steel for both the races and the balls to get good life and handle large loads. These balls are in some kind of a cage that separates them and keeps them located appropriately around the circumference, and the balls do not rub on one another, so there's airspace between the balls maintained by the cage. And because there is this little bit of a wraparound, this bearing can take some thrust load as well as radial, but they're primarily designed for radial load. And they can take thrust in both directions. The so-called angular contact ball bearing, you'll notice, only has a wraparound on one side of the ball, on this side on the outer ring and the opposite side on the inner ring, So that can obviously only take thrust on the outer ring to the right and not in the other direction. And also, of course, can take radial load. So it says over here, deep groove, which is the one on the left, are selected for radial and moderate thrust or axial load. Angular contact are selected for radial load and larger thrust axial in one direction. So there's more wraparound apparently here on the ball that lets that take a larger thrust load, but only in one direction. Here's the tapered roller again, a conical shaped roller arranged so that it can take both directions of load. Another nice feature of the the tapered roller is it's separable. So I can pull it apart and have the outer race in one hand and the inner race in the other. And the rollers will be attached, I think, to the inner race, usually, and the outer race is just the race. Whereas ball bearings, typically, you can't take apart, or you'll ruin them if you do, because they're crimped together. And likewise, this type of spherical roller bearing, you would not be able to disassemble. So they're made to be pressed on the shaft and into the hole. So the bearings are made with very tight tolerances on the OD and ID, suitable for press fit, which makes them easy to put in and hard to get out, as you might imagine. So quite often you will press only on one or the other, press it on the shaft, and you'll clamp it in. I'll show you some clamping arrangements later on the other side. So I have some means of disassembly for replacement purposes. This spherical roller will give me some self-alignment capability, which is nice. Most of these bearings will require you to have very accurate alignment of your shaft holes so you don't put side loads on the shaft and bending moments. But there are some, such as this spherical roller, designed so that the outer race can rock with respect to the inner race and self-align. And those are nice because I know I have simple support at the load then, since it can't take a moment, right? Then if I have strictly a thrust load, there are two possibilities here. This shows a ball thrust bearing. Again, the balls are captive in some kind of a container called a cage. And we have an inner and an outer ring, which are really a top and bottom in this case. And this is a roller version of the same thing, a thrust roller bearing. And these will have more friction because, as you can picture, if this is a cylindrical roller, it cannot have zero slip except along one line because I've got a different linear velocity as the radius changes. So there's going to be some sliding going on here, whereas the ball has point contact, so there's less sliding involved there. These will hold very large loads. So this is a list of pros and cons for rolling versus sliding bearings. There's always a trade-off in some respect. So the rolling have advantage over the ones we talked about the other day, sliding or journal bearings. Very low starting friction. In fact, you're familiar with the Coulomb friction idea that there is a static component of friction that's larger than dynamic, and that's true whenever I have something sliding on something else. So that's a characteristic of a journal bearing. So it takes more torque to start it rolling than to keep it rolling. Whereas a ball type interface or a roller type interface, there's very little difference, almost immeasurable difference between the static and the dynamic friction. So they start up more easily than a sliding type bearing. Interesting little tidbit as a side note is that around the turn of the 20th century, the late 19th, early 20th century, railroads switched from journal bearings in all the axles of the train cars to ball bearings. And long freight trains that originally required two engines to get them started because of the start friction could then be run with one engine. So it was a huge saving in fuel costs and so forth, and equipment being tied up, if you could run the same length train with one engine as opposed to two, just because they put ball bearings in all the axles. The journal bearings typically cannot take any axial load at all unless you make it. It's either one or the other. You can make it be an axial or you can make it be a radial, but not generally both. This is less sensitive to loss of lubrication. It's very stable dynamically. I didn't talk about things like oil whirl and so forth, but you can develop some dynamic instabilities in a journal bearing that have to do with the oil essentially whirling and vibrating within the interface. Good temperature stability. They're sealed to be lifetime lubricated. They don't take up as much room in the axial direction. They're quite thin. But on the other hand, as we'll see in the other list, they take up more radial direction because a journal bearing can be very thin, as you saw with the Babbitt in your auto engine. It's just thousandths thick, actually. Whereas a radial bearing got to have room for the balls, the rollers, or whatever, and it's going to take up more room. So the outside diameter gets bigger. Disadvantages of rolling: we're going to have fatigue failure eventually, which I don't face in the case of the hydrodynamic bearing. That can theoretically go forever unless I get dirt in the oil or do too many starts and stops when I'm rubbing metal to metal. So if an application like a power plant, where the turbines and the generators run round the clock without stopping except for occasional maintenance or power failures or whatever, those bearings should really never wear out because they're always running with clean oil. Poor damping characteristics. The oil film in the journal bearing gives me a good bit of damping, so that absorbs some vibrations, some shock loads. Whereas the roller bearings are really metal on metal. I can't get these up into EHD lubrication typically. Higher noise level, because the balls and rollers rattle a bit, so you hear them, whereas a journal bearing is dead quiet. Doesn't make any noise at all. In fact, when you are concerned about vibration in a machine, I've built a number of test rigs down in the lab to do vibration testing over the years, and I never put rolling element bearings in them, because if I'm trying to measure vibrations on some other part of the system, like maybe a cam follower or something, and I have rolling bearings in there, I'm going to be listening to the rolling bearings instead of what I want to listen to. So I always make those with sleeve bearings, even if I have to run them in boundary lubrication and suffer the wear, because I'm not going to bother with the oil pump and all that stuff. So I just use an oil can to oil them. So they're in boundary lubrication most of the time. Higher cost. It's pretty obvious that a slug of bronze is going to be less expensive than something with a bunch of balls in it. Higher friction. Because when I get up on that oil film, my friction coefficient drops very, very low, even lower than the rolling. This is, we saw some of these in an earlier picture. This is a catalog page right out of a bearing company's catalog. And here are some of the big manufacturers, SKF. They seem to like initials, FAG, NTN, Timken, and there's a whole bunch more. So you can go to their catalogs, which are now all on web pages, and you can find out all the information you need to specify a bearing. Very rarely, unless you work for a bearing company, you'll never design a bearing. You'll simply select one from the available bearings, and we'll talk a bit today about how to select them properly. It's quite straightforward. We know that in surface fatigue, it's eventually going to fail. It's only a question of how many cycles does it take to kill it. And this curve shows a statistical distribution, in essence, of the rate at which the bearings will fail in service. And it's referred to as a life distribution curve. On the horizontal axis, we see something called relative fatigue life. And the reference life is this so-called L10 life, which is given a value of 1. And for a given bearing, that will be a certain number of cycles under a certain load. And what it means is that you can expect that 10% of your bearings will fail in that many cycles, whatever this represents in an actual calculation. And 50% of them will fail say this turns out to be a year to make it easy to talk about. So say this is a year's worth of running. I'll lose 10% of them. In 5 years, I'll lose 50% because this is fairly linear right here. Then the curve goes nonlinear, so it'll take me 10 years to lose 80% of them, 15 years to lose 90% of them, and 20 years to lose almost all of them, like all but 5% of them, or something like that. So the L10 life numbers are used as the reference, and that's what you'll find in the bearing catalog. And with a very simple formula, we can calculate for our load how many of these lifetimes, these L10 lifetimes, should we expect. In other words, where are we on this picture here in terms of number of cycles? That's pretty straightforward to do. This is the relationship that's been determined by experimental data done by the bearing companies in large part. And it's slightly different for ball and roller. L in this case is the fatigue life measured in millions of revolutions. C is a dynamic load rating, which is a number in pounds that is assigned to each bearing based on experiment and testing that they've done. So each different size and type of bearing will have a different number for C. And P is the load that you're going to apply to the bearing, whether it's be radial or axial. This allows me to combine the two. So this is the equivalent applied load. And if I have a combination of axial and radial load, then this equation will let me find what P is for the given combination, where FR is the radial load that I'm applying, FA is the thrust load that I'm applying, and these factors X and Y also come out of a chart supplied by the manufacturer along with this factor C. So I can look up the X, the Y, and the C, and V is the rotation factor, which is 1 if the inner race is turning and something a little bit bigger, I think, if the outer race is turning. So the reference is for inner race to be turning. And that's about it. So I can get a number on P based on my applied loads. I go into the table for the bearings. If it's a roller bearing, it's 3 1/3, 10/3 instead of 3. I know what my P is. I look up the C, and I get L, which is millions of revolutions of life. And if that's not long enough to satisfy me, I go back and probably grab a bigger bearing, which will have a higher value of C, and find something that will do the job. This is just a little snippet out of one company's bearing catalog. Bearing numbers will be different between companies, but they'll all have something equivalent. So they tell me the bore, which would be the ID. They tell me the outside diameter, they tell me the width. They tell me what size snap ring to use to hold it in, if I'm going to not press both halves in. They tell me what the fillet radius is that I have to put on the shaft, which of course is going to affect my stress concentration, because I have to have a shoulder up against which I'm going to push this. Give me approximate weight of the bearing. These are small bearings. They give me a limiting speed in RPM. And here's that C, which is the dynamic load rating in pounds. And this is just a reference number. It doesn't mean that I can put 1,930 pounds on this particular bearing. I might, in fact, fail it statically if I do. In fact, the static load rating is only 1,200 pounds. So that says for that bearing, I don't want to put more than 1,200 pounds on it, because I'm going to dent the race with the balls, essentially, at that load. The 1930 is going to be used in that formula to calculate what my projected life is with my load P. So P is going to be a fraction, typically, of C. Okay? And that's really all I have to do is select these data out of this chart and then apply them to that equation that we just looked at right here. That would go in for the C. I know the P. Get my life very straightforwardly. Now, fairly recently, I didn't put a year on this, but this is only in, I think, the current revision of the book, so it's only a few years old. ASME and some other researchers have come up with a new standard. It's both an ISO standard and an ASME standard for rolling bearing life. And what's happened is there's been something of a revolution in steel manufacturing over the past couple of decades. And they've they've discovered how to make what they call clean steels. And by clean steel, what they mean is they've controlled the process to such a degree that they are keeping the debris, the crud, out of the steel. And it's the non-steel components in the steel, that is pieces of dirt or little gaps, that cause the cracks to begin forming. The cracks will start forming at one of these disruptions. So if you could somehow make a piece of steel that had no defects and no foreign material in it, then you theoretically would have a much stronger material, and it turns out that you can approach infinite life in surface fatigue with these special clean steels. So, as I underline that here, it makes use of the latest empirical data on the surface fatigue strength of bearing steels. And these are being applied particularly to bearings where you're trying to get longer life. And it's simple enough to use. It's not easy to calculate, except for the fact they gave us a program from ASME to do it. But they've created this multiplier factor, A sub SL, which you multiply by the L10 rating for the bearing to come up with a modified ASME, different L10 rating. And if you use that instead, you'll get a more accurate calculation of bearing life in the equation that says L is C over P. And it says here, ASME has published this in reference that I give you in number 30, and it's a very complicated algorithm, but it comes with a computer program called ASME Life that calculates this number for you for any set of loading and environmental parameters. They explain the algorithm, but it's rather complex, so I didn't even try to include it. But if you get the software package, you don't need the algorithm. So for the purposes of my chapter, I've just considered this to be one. And you can go to that reference and pay them a small amount of money and get that program to do more accurate calculations if you would like to do that. This is an example that I have in the chapter. I'll just walk you through it. It says we want to select a deep groove ball bearing for a certain loading in life. Now in your case for your project, you've got mainly thrust load, I think, right? You've got the weight of all that stuff sitting on at least one of your two bearings, right, to support the weight of the dial. And you don't have an awful lot of radial load, I don't think, because you're mainly transmitting torque. And unless things are out of balance, which they don't want to be, up top, I should not have an awful lot of side load. So you're really in mainly a thrust situation there. So I don't think you're going to have any difficulty whatsoever in getting a bearing able to handle this, because your shaft is so big due to the stiffness requirements. It's going to drive you up to a very large bearing, much bigger than you need for the loads that are on the bearing. And you're probably going to have, 10 to the 12th cycles kind of life is my prediction when you do these simple calculations. So that's going to be fairly easy for you to deal with. Your main issue is going to be finding a bearing that fits your particular situation for your geometry. So in this example, I said I'm going to use a deep groove, which may or may not be what you want to use for your situation. There's a stated radial load and a stated axial load and a shaft speed, and the conrad is specified. Inner ring rotates, and we want to get at least 5 times 10 to the 8th revolutions. So I go into the chart and I pick a bearing to try. And the way I set this example up, this turns out, I think, not to be sufficient, and I have to go back for a second round and try a slightly different bearing. And so I get out of that chart, I find its C is 21,200 pounds, and its C0, this is the static load, is 18,000 pounds, and the maximum RPM is 3,800. Well, that's certainly fine because I'm going 2,000. So here's where those numbers are coming from. This is the same chart I just showed you a piece of. So this is a 6316 bearing. There's the dynamic load rating. There's the static load rating. Limiting speed is there. So I take those numbers to my equation. I want to find out if I have a static problem, so we calculate the ratio of my axial load to the static load rating, C0, and that's 0.056. I go to figure this is from an earlier edition when this was chapter 10, so it's really 1124 now. That's what the notes say. And I pull out a value. So this, we're looking now at another chart from that same manufacturer's catalog. And we go in and form this ratio, FA over C0. We got the C0 from the other part of the chart. And we find that it's, we calculate that at 5.6. We come in and find that value. And we look over here, and that gives us an eccentricity, an E, of 0.26. And we then compare this number, FA over VFR. This brings in the inner-outer race business. I said inner race was turning, so V is 1. And FR is our radial load. So this is the ratio of the axial to radial load. And these were the numbers that were stated in the problem. And that turns out to be 0.6, and that's bigger than this E factor. And because of that, here's my 1 for V. Because that's greater than E, I want to extract the X and Y factors from this figure, which are given to me here. There's X, I think, and there's Y up there. This 5.6 applies to all of these values. So I'm getting my X and Y now out of the chart to use to find the equivalent load P, which turns out to be that value. And I use that in the equation, C over P to the third power, and I find I have 5 times 10 to the 2 millions of revs, which is 5e8. So I guess this did come out. Oh, I say here I did some iteration. I only showed you the last one. But I do remember when I did this, I had to go to the chart a couple of times and try different bearings, which is typical. So this was my last selection that actually did work and gave me 5 times 10 to the 8th revs. Remember, this number's in millions of revs. So I got 5 times 10 to the 2 times 10 to the 6 gives me the 10 to the 8. All right? That pretty clear? I think I showed you this in an earlier lecture, actually. This looks familiar. Different ways of capturing bearings. Here, they're using a nut on a thread to guarantee that this thing can't work its way off the shaft. This means I don't have to have as heavy a press fit. I can have just a nice sliding fit there. This is using a snap ring to hold it in instead of a nut. And this is also using an external cap which is pushing on the outer race. So this bearing would probably come right out very easily because I don't think there's any pressing involved. It's being captured both on the inner race and the outer race axially, so it can't get away. This is a similar arrangement here. There's a spacer in here that's going to keep this inner race from moving to the right, and there's a cap that's going to grab the outer race. And that set of little circular things there is an oil seal. So it looks to me like this is intended to have an oil bath, so there might be an oil supply to this somewhere that keeps this wet with liquid oil rather than grease, and these seals that prevent that stuff from leaking out to the outside world. I think I did mention when we talked about shafts that you don't want to have 2 axial locators on the same shaft because the shaft will expand when it gets hot, and that's going to give you some additional loads in the balls which will shorten their life. So in this case we have the bearing on the left is not locked in an axial sense to this outer race is not locked. It's free to move in response to thermal expansion. In other words, this thing could grow and shrink and not move the bearing with it, whereas this one is caught. So this end is what's keeping the shaft in axial location, and of course I need a second radial support to give me the moment on the shaft. It's quite common in machinery to buy a pre-packaged arrangement. This is called a pillow block, and this is a flange mount. And inside each of these is a ball or a roller bearing. You can get almost any type. You can get self-aligning if you want. and they come with a handy mounting kit so I can bolt this down to a horizontal or a vertical surface for that matter. They have a built-in grease fitting for relubricating the bearing, and this bolts up to a sidewall, supports a shaft going through to the other side of the machine or whatever. Cam followers are essentially bearings that have been packaged in a way that makes them convenient to use for a cam follower. Threaded rod typically, with a nicely ground surface, dimension carefully controlled here, and not visible as shoulder. So what I would do is ream a hole to be a good fit on that barrel, and with a little bit of a flange here to support it, shove that in, put a nut on it, and sock it down so it can't get away. Rod ends, purchase parts, they're typically a one spherical bearing, like a truncated sphere here with a hole in it, and you could put a shoulder screw through for a pin or an actual pin with snap rings. And this is self-aligning, and this end is typically threaded, so I can thread a rod into that, and I can make a link very quickly, and it's even adjustable as to length. Very commonly used in machinery. So which do I use where and when? One thing to keep in mind is, one thing rolling bearings don't like to do is not go around in full circles. You should not use them when you're oscillating, because in essence you're going to just wear a groove, and the same ball is running against the same piece of race all the time, and they're not going to survive anywhere near the life that's predicted if they're turning continuously. So if I have continuous rotation, then rolling element bearings are okay. But if I have oscillation, then I'm pretty much stuck with journal bearings. I'm going to have a higher starting torque with journals. I've got to be able to deal with that, provide it in some fashion. If I can't stand that, then the rolling is going to give me a low starting torque. I need lots of lubrication for a journal bearing if I want it to last a long time. Maybe I can't stand to have the oil all over the place or leaking. Now I can get this so-called lifetime lubrication that's trapped in within the seals of the bearing. If I want to float something up on a hydrostatic fluid with air or water, like we discussed the other day, the obvious choice is a journal, which in this case would be probably something flat. Accurate location is easily obtained with rolling. If I need preload, and preload is something that is often used. In fact, the bearings on the shaft that you're designing are actually heavily preloaded, and that's to take out any possible slop in the shaft in any direction, either vertically or sideways. So by preloading is meant that when you assemble the bearings using a nut or other means, you actually jam the two bearings. You use a double row bearing and you put them together with some force. So I can't get any error in position. The journal type will not give me both radial and thrust. I can only get one or the other. So if I need the combination of both, then it's obviously we need a rolling bearing. If I want stock replacement, most of the journal bearings are custom made. They're just a piece of metal that's made to fit whatever the application is. However, I can split the journal bearing for assembly purposes, and that's true of your engine bearings, right? If you've ever taken those apart, you have bearing caps. Turn the engine upside down, take the bearing caps off, lift the crankshaft out. If I have ball bearings, I got a big problem getting that thing apart, right? Or even getting it together in the first place. In fact, it's just about impossible because I've got bearings in the middle of the crankshaft. How do I get those on? I can't make them go over the cranks very well, so I'm pretty well stuck with using a split bearing, which rules out ball bearings. So you almost never see ball bearings in the lower end of an engine. I have seen it in some motorcycle engines, 2 cylinders, singles, and they use a split crank. So the crankshaft comes apart axially in order to get the bearing on the crank pin, which is a bit of a do. So you have to have some way of fastening the crank together that will stand the loads, which are significant in an engine. I've only seen that in a couple of off-road bikes. I don't think it was very popular. I need to assemble these guys axially. I'm talking about the same thing here. I can't put them in sideways. And the big advantage here is I can get them off the shelf, and I can stock spares. So if one wears out, I can quickly swap them and keep my machine going so I'm not losing production and so forth. So they're very different animals and have very different applications and very distinct pluses and minuses. And both work very well for whichever situation that you find yourself in. And particularly for rolling bearings, since they are standardized, you typically rely on the manufacturers for advice in selecting them. And they don't want you to select the wrong bearing and have it wear out and give them a bad name, so they will, in essence, offer you free engineering help through their sales organization. So you should definitely avail yourselves of that. And even for your project, you can get a phone number off the web, and there's loads of them in this area. Right in Worcester, there's some bearing operations. You can call them up and say, I've got an application of, here's my loads, here's my conditions, what kind of bearing do you recommend? And you'll learn a lot from them in a very short time. And they'll sometimes even do a calculation for you. I want you to do the calculation in this case, but in the real world, when you're under the gun for a deadline, you'll take all the help you can get, right? So if someone's willing to help you do it, fine. I give you the SKF site, and you can find others. We've got some of them on the Mighty BPI site, but if you simply Google roller bearings or ball bearings, you're going to get hundreds of them. Any questions on that? Short lecture. There's not much complication to roller bearings. Questions on the project? Yes, Joe. The preloading of bearings? Yeah. It's typically done when you want to have very accurate location, particularly in the axial direction. So rather than allow the bearing to be sloppy on the shaft, I'll load it up in one direction. It also takes out any clearance in the bearing. If you think of those angular contact bearings, they're like this. If I load this one this way, I take all the wiggle out of the ball and the groove. Okay, that's really what I'm doing, is I'm eliminating all of the possible, and it's small to begin with. It's probably 1/1000th of an inch that's built into the bearing. And I'm actually potentially reducing the life of the bearing by doing this because I'm increasing the load on it, right? But I'm willing to trade that off for no wiggle. So I have absolutely zero play in the system. And that's the reason it's done in that particular application. They don't want any play in that thing. So it's fairly commonly done.